Hello, hello. Can anybody hear me okay? Give me a thumbs up. Okay, got it. Cool. All right, we're going to talk a little bit about event-driven architectures. My name is Kenny Gorman. I'm the head of product management for the streaming products here in MongoDB. And let's just jump into it. How many people here know what an event-driven architecture is or use one? How about use Kafka? More people. Okay. Yeah, so these are the things we're going to talk about a little bit today. That gets me started so I know kind of where you're at. All right, so we're also going to talk about a bunch of future things that we're doing. So a little safe harbor statement. So yeah. All right. So we're going to talk a little bit about the problem with event-driven architectures. I'll talk about what they are a little bit, just fill you in. Then we'll talk about a couple common problems, common issues. We'll talk about just a general solution. And then we'll talk about Atlas Stream Processing and how it fits into that picture. Second to last, we'll talk about building a stream processor, how to do it, how easy it is, what they do, how they work. And then we're going to talk a little bit about architectures that are enabled because of this. So once you build a stream processor, what can you do now with event-driven architectures you couldn't do before? All right. So let's just kind of level set here. So maybe 10 years ago, 15 years ago, a while ago, databases it was common to have a database and an app, and that's it. It did a thing for the business. The data came into the app. It went into the database. It was persisted there. It came out of the app and did something. Okay, pretty simple. Maybe we all lived in that world. I lived in that world. But now it's quite different, right? The Mongo database or any database that lives in the ecosystem of an organization, corporation, whatever, institution of some sort, oftentimes has data coming in and out of it for some business reason, right? So data's flying all around these days. It might be used on a Kafka event bus. It might be coming in through some sort of IoT channel. It might be going out to OLAP products. It might be going across to different regions for materialized views, something like this. Tons of different use cases, and data needs to move between systems. And the reason the world built event-driven architectures is they have some benefits. So number one is scalability. That makes sense. We're moving data to different systems. Those systems have different compute capabilities, make it easier to read and grow your systems, better performance. But it also enables more timely response, right? So even coming here today, I had an event-driven architecture, product happen. I was using the United app, and our gate changed, and it immediately let me know that gate changed, and I went ahead and walked to the new gate. That kind of experience where the timeliness of data matters, if I got that data 15 minutes later or a half hour later, it's kind of useless, right? And now I'm a mad customer. So these kind of experiences, event-driven architectures enable. But they're also fault tolerant too. So you can copy data to maybe a different geo, maybe you're using separate systems altogether for different parts of your organization. Imagine again, the airline use case. I've got a customer data system. I've got the accounts data system, maybe the miles data system, and they all have to communicate. That's an event-driven architecture. But there's some problems, right? We went to this cool thing. We got all the scalability. We got this event-driven nature of our application. But how do we efficiently capture and process data between these systems? How do we guarantee consistency? How do we know the data is right between them? And as we add more things, inherently it gets more complex and it probably costs more, right? So there's some downsides too. There's definite trade-offs to event-driven architectures. Generally speaking though, the solution is, hey, we may have a data system A, B, C, D, whatever it might be. I talked about like Miles database and customers database and things like that. But generally speaking, a stream processor is an integral and important component in this ecosystem. In other words, how do I get the data from A to B? What's the pump pumping the data? What's the thing pushing it out of MongoDB, say, and into Kafka? or the thing reading from Kafka and sticking it into your collection? How does that work? And when you do it, a good stream processor will allow you to do transformations. Maybe you're redacting fields that don't need to be in one system or another. Or maybe you're concatenating things or doing math, arithmetic, or something on a field. Maybe you're aggregating. Maybe it's like a materialized view, something like that. And it's continuous. That's the other thing about event-based systems is it's continuous. Events are always happening. So you have to have a system that can handle this continuous flow of events coming through. Maybe it's from a Kafka bus or something like that. How do you handle those, deal with those events, and then do something with them for the business? And of course, none of this is useful without it being low latency. So the example I just talked about, if it takes a half hour to process my gate change, it's useless. And these things are always on. They're always capturing events. They've got to continuously run data from A to B in the system, never stopping. They never sleep. Okay. And at the end of the day, I gave a couple examples, but it's more broad than that. It's not just the airline reservation thing, obviously. It's, how do I work with IoT systems, manufacturing systems, supply chain problems, connected cars, aerospace, on and on and on. Just about every use case these days has some sort of data in motion or data moving. All right, so our solution is Atlas Stream Processing. That's the way with MongoDB that you connect to this larger ecosystem of systems and process the data for the customer. Okay, so it's a unified approach. It's built into Atlas. There's no extra components or extra things to buy. It works like the rest of MongoDB. I'm going to show you in a minute how the language is constructed, how you can write a stream processor. And it scales, it's monitorable and observable, just like the rest of Atlas, and generally works the same way. And here's how it sort of fits into the Atlas profile in the sense that, like, Atlas Stream Processing is no different than, vector search or any of the other components that fit into Atlas. You'll see it on the side tab, and I will encourage you after the talk to go check it out. Go to the side nav in MongoDB Atlas, click on Stream Processing, and get started. Okay, so what does it do? Well, it's based on MongoDB, but you should know that. It's built on the database that we've had around for a decade. Okay, so it's not a net new piece of technology. But it's much different in that it runs these queries continuously. So you're going to write an aggregation in the aggregation language. You're going to launch it like a job, not like a regular query, and it's going to run continuously. So remember, when you run a query or an aggregation in the database, what does it do? Well, it goes out, it reads the data, might use an index, finds the data, returns the data, and then quits. It ends. Returns the data to you, and you're done. Query over. Stream processing doesn't work that way. Stream processing sits there and continuously is pulling that data from the source, whatever that might be, and pushing it to the sink. So a stream processor, I said, has to have that attribute. Atlas Stream Processing has it. And then you want to be able to compose pipelines. So it wouldn't be super useful if you just took data from A and shoved it to B without anything in between. So composing a pipeline, building a pipeline in a language that allows you to express whatever that transformation is super important. I'm going to show you that too. So Atlas Stream Processing allows you to write a pipeline, an aggregation pipeline. It has a new thing called a source and a sink. And I'll show you how that works. And it's taking data from the source and moving to the sink and allowing you to put a transformation in the middle. All right. Just to point out, it also allows you to enrich that data. We have new operators that allow you to read into a database. Maybe you're joining data in a stream. Maybe you're reaching out to an external service. I'll talk about a couple of those calls here in a minute. All right, so this is kind of the general architecture. It might be hard to see it if you take a pic. Yeah, use your phone. Yeah, there you go. Yeah, okay, perfect. But let me walk you through it, okay? So we're going to start on the left, and we're going to go to the right, all right? So let's talk it through. So this is like a connected car example, okay? So squint with me, bear with me a little bit, but this is how it works. So on your left, you've got the car and it's emitting some sort of telemetry data. Maybe it's fuel mileage, or maybe it's battery level, something like that. And then maybe you're putting it into a Kafka topic. Maybe you're using Confluent Cloud, right? You're just piping the data from the car into Confluent Cloud, and it's in a topic in Confluent, in Kafka, and now you need to read it, okay? Or maybe it's some other use case where you're writing it directly to MongoDB, and then we can read the chain stream. Okay, so that second box there next to the car, I'll have a pointer, otherwise I'd point, is the layer, the event layer ahead of Atlas Stream Processing. So that's the source. Next, you compose a processor, you write your pipeline, and you start that as a job. And this is where all these operators, where the pipeline comes into play. So how many people have written aggregation statements? Just raise your hand if you use. Okay, nearly all of you. Okay, so every one of you is now able to write a stream processor, just so you know. When you leave here, you're going to be a stream processing expert because you already know how to write an ag framework query. It works exactly the same way with kind of two differences. The first is the first stage is the source. Kafka, MongoDB, Kinesis is coming soon. The last stage is the sink. So also could be MongoDB, also could be Kafka, also could be Kinesis coming soon, maybe S3, things like that. Okay, that's it. That's the mental model. I'm writing an aggregation. It's going to run continuously, reading from a source, writing to a sink. A couple more capabilities just to kind of point out. As I said a minute ago, you can reach out to an HTTPS endpoint. So maybe I'm reading some data and I'm looking for, I don't know, a weather pattern. And in that weather pattern, I'm finding something really bad. I need to text people. So maybe I hit Twilio, right, via API. So I could do that. I could call out in my pipeline to HTTPS endpoint for Twilio, send them the API key, send a text. Or maybe I've got a microservice. Maybe you see fraud data coming in, okay? And you've got a microservice internally, and you need to hit that microservice and turn off an account, like, stop the customers, cancel the customer. So you could do that as well, things like that. We also support Lambda functions. So you can call out database Lambda. If you have an investment in Lambda, so you already have 100 Lambdas out there or something, you've built your business around Lambda, you can plug right into this, use all those business functions. All right, couple things to point out, just a couple nuances here to make sure everybody's clear. Number one, this does not replace Kafka. This works with Kafka. This does not replace Kinesis or S3 or any of these things. The goal here is to work within that ecosystem, to be a better partner, to be a better component in a larger event-driven architecture, okay? So we're adding more sources and sinks over time to make it work with a whole bunch of different things. Today we're on AWS, we're on Azure, and GCP was just launched. All right, let's talk about building them. I talked to you a little bit about it, but what does it look like? Let's break it down. So that's it. That's a stream processor right there. And just to kind of give you a feel for it, in other frameworks, other popular frameworks, a stream processor would not fit on this page. It would be many, many, many lines. Number two is you'd probably have to know a lot about streaming. You'd probably have to know a special API. So this is, for MongoDB, this is it. It's an aggregation statement. Should look super familiar. I'll point out that's a piece of JSON, right? There's a curly bracket starting it and ending it. It's got a name, okay? So that's the processor name. And then it's got a pipeline. And that pipeline is the aggregation statement you're so used to. Okay, so in this case, the first, like I said, is $source. Let's just kind of go through it. $source, it's got a connection name. That name is a logical name you set up in the connection registry. That registry has all the creds for how to connect to that and gives it a name. So it knows how to connect to, say, Kafka in this case. Actually, in this case, it's database. So let's just keep going. It specifies the database and it specifies the collection. So it's going to read the change stream for that collection. Everything that's going into that collection, it's going to look at the change stream. It's going to do change data capture, and it's going to push that data through the stream processor. The next stage here is match, $match. We're taking the full document. coming from the chain stream. If you've looked at a chain stream before, you'll know what full document means. It's just how things are arranged in the resulting document from a chain stream. And we're actually looking for a total where it's greater than 100. Okay, so typical match kind of thing. Then we're adding some fields there. Okay, and then it's got a conditional in there. And then lastly, we're merging it into another database. So maybe in this case, it's a Mongo to Mongo use case. Like I said before, a source can be Mongo and the sink could be Mongo. Maybe they're in different geos. Maybe you're doing an aggregation and storing materialized views. Maybe you're redacting data for compliance reasons, that kind of stuff. That's it. That's a stream processor end to end. And you have a rich set of operators. Don't try and read every one of these. This is just not even all of the aggregation operators. I couldn't fit them all on here. But there's a ton of capability within the ag framework itself. So if you need to do mathematics, you need to do like arithmetic and things, you need to do conditional operators, you need to concatenate, all that stuff is available. Plus, we have a whole bunch of ones that are stream processing specific. So source and sink, sources and the sinks are obviously specific for stream processing. The way that the source is called source, the sink is called merge or out. Emit, excuse me, not out. And we have window functions, so tumbling windows, hopping windows, things like that. If you're familiar with stream processing, you'll know what that means. Essentially, it's just an aggregation type of window. We have the ability to do validate. We have we have lookup, $lookups. You're able to look up into a database, enrich that document, and push it along the pipeline. We just added cached lookup, which is now an LRU cache on the lookup. It's a whole bunch of tools for you to build your own statement. Even further, we now support $function. So if you want to write a bit of JavaScript, maybe you have something that, like for instance, if you're familiar with doing geomath, let's say you have a lat and a long, or two pairs of lats and longs, and you want to compute the distance between the two. You might use the Haversine formula, if you're familiar. It's a bit of math that can compute the difference between those two. You could put that in $function. You could have your geo lat longs for the distances between, I don't know, your hotel room and the bar, and you could be computing the distance between that in real time in the stream. Okay? Don't need any other stuff. You can just do it right in the aggregation statement. $function gives you that capability to write a bit of JavaScript and put that right in there. Otherwise known as a user-defined function if you're familiar. And like I said before, Lambda. So maybe you have that Haversine formula in a Lambda out on AWS, and you're like, hey, I want to call that. And you can do that as well. All right. Let's talk about the development environment. You might say, cool, how do I write these things? So we're starting simple. We've started simple, and we're starting to do more and more and more capabilities here. First of all, we did Mongosh, as you might expect. You'd want to use Mongosh as kind of the first touch point, but we've gone way beyond that now. So VS Code is a very popular IDE for writing code. And I'd like you to think about stream processors more like code, not like queries. You know, in SQL land, we might say select star from table or something like that. It's really just a statement, right? It's pretty simple. You don't necessarily need an IDE to keep track of that. But as you start to write these stream processors, you're going to want to be more and more expressive, adding more and more capability. The IDE is a great way to do that, and it enables Copilot type tooling. So today you can use Copilot with Atlas Stream Processing. With a few strategic hints, it works great for actually using AI to create processors. And it's a great way to build an environment and create processors. So we have that. Also, by the way, it enables you to save your files in Git and use your standard Git workflows. We have an admin API. So that API allows you to just go ahead and create, run, and manage stream processors from the admin API, as well as Terraform. And then we just released this week a UI builder that's right in the UI that allows you to drop in two things. Allows you to drop in a processor like I showed, as well as build one incrementally. So it allows you to say, hey, here's my source. here's my, processor in the middle, and here's my sink. Go ahead and start that and start moving data. So that's kind of the development environment. Okay, so that gives you the background there. Let's talk about a little bit about what this enables. Where can we go from here? So we're building these stream processors. We're running them on Atlas. It's moving data from A to B. We live in an event-driven world now where we have to move data all around. One of those use cases is moving data to OLAP systems. So very common to say, hey, I want to subscribe to a change stream on a collection or many collections, maybe a whole database or a whole cluster. And those changes, I want to go ahead and push downstream to some sort of OLAP system. Maybe it's Snowflake, Databricks, something like that, okay? So how would you do that today? Well, today it's complicated. There's a lot of steps. So I said one of the downsides of event-driven architectures was it gets complex and it gets expensive. And so we're working to reduce the number of steps. Now that Atlas Stream Processing has all these capabilities, we can collapse a lot of the stuff and make this architecture much more simplistic. Can everybody see this? Raise your hand if you can see. Okay, perfect. So let me walk you through this, and then I'm going to walk you through where we're going. Okay. So on the left, we'll do the same left to right thing. We have MongoDB as a OLTP data store. Okay, so maybe this is transactions coming in, financial transactions, or whatever it might be. The data is being written to MongoDB, and that data is in the change stream. Okay, so a common way to do this up till now, for the last few years, is to say, hey, okay, I'm going to put a connector on MongoDB, and I'm going to listen to the change stream. Then I'm going to take everything that comes to the change stream and I'm going to put that into a topic or many topics. So one common way is to say, like, for each collection, there's a topic. Okay. Then maybe I write it to an S3 connector. So I got another connector and I'm going to write it to S3. So maybe it's one document per message. So it's a lot of data on S3, but okay, it's out there. Then I might use something like Snowpipe to go read that S3 repository, take all that data, and start to load Snowflake. Except it's all the data. So it's very common to use the medallion architecture, medallion design, and say, okay, let's graduate it through 3 different stages. Let's aggregate, parse, mutate this data, redact, whatever the business process is that needs to happen, graduate that data, and then present it in Snowflake. So finally, someone's reading it. That is a lot of steps. There's a lot of things to monitor. There's a lot of things to manage. There's a lot of things to go wrong. There's a lot of things to introduce latency. There's a lot of complication in that stack, cost and complexity. So can we make this better? Yes, we can make it better. So this is where Atlas Stream Processing plugs into an event-driven architecture and simplifies it overall. Okay, so let me walk you through this. Again, on the left, we have the same OLTP database, but now we have Atlas Stream Processing. Now we have additional capabilities. We're processing in MongoDB. We're not, creating some job or some framework, or we're definitely not doing it on Snowflake. We have the ability to process that data with all those operators I showed you and more. Maybe what I'm doing is I'm saying, hey, I want to see all the things coming through in this change stream, and I want to score them using an LLM, and I want to see the sentiment, not only the sentiment like, positive, negative, neutral, maybe I want to see the reason why, and I want to do a sampling. LLMs are really good at that. So maybe I want to do that on the stream. I want to enrich the stream and then push it out to my OLAP system. So what we've come up with is, hey, let the Snowflake or Databricks or other teams have their systems. We're not going to, try and change them. Let us have the OLTP system and the ODL on our side, MongoDB, and let's have this middle layer called Iceberg. Okay, so if you're not familiar with, who knows what Iceberg is? I'll just raise the hands again. Okay, let's talk about Iceberg real quick. So Iceberg is a table format. It lives, in this case, on something like S3. It's just files on S3, okay? But it's consistent, and it has a schema. Open source table standard. And things like Snowflake and Databricks and others can read it, have APIs to read it, and now we have an API to write it. So if you're using those systems in-house, who's got Snowflake or Databricks? Okay, so this would be something you should be looking at. How can I simplify my stack? How can I make it easier for that team? I'm assuming you have a team that deals with that. How can I make it easier for that team to read the data from MongoDB? The answer is Iceberg. This is often called shift left, if you're familiar, meaning I'm going to shift the processing power, the processing burden to the left of the diagram. Oftentimes the OLTP part or online data store is on the left side. That's all it means. We're shifting it to the source. It's going to be less expensive, more performant, and you don't have to have that many copies of data. So today we're announcing $Iceberg, yet another stage, a sync, that allows you to write Iceberg data directly from MongoDB and Atlas Stream Processing. So now you can specify a new stage. You can take your event stream coming from MongoDB, write it to Iceberg, and achieve that architecture that I just shown. All right. Just a couple things there. Just kind of as a how it works thing. Two things that are important here is that it's going to live on S3. So it's being released on AWS, S3. You give it a bucket name, you give it a database name, and you give it a connect string in our connection registry, and that's how you know how to connect to it. So now you basically have democratized that data, so to speak. You've moved it out as a data product to your other teams for consumption in this standardized, easy to read open source format. So I'm going to end early, so I expect lots of questions. Few things that I want you to think about. So overall, this discussion is about cost and complexity. Event-driven architectures typically have a lot of benefits. We talked about them, but they also have the downside of cost and complexity. And Atlas Stream Processing can help you reduce the number of steps, the number of components, the amount of monitoring, the fragility and brittle systems, and pull it into Atlas. We allow you to build those with familiar tools. Almost all you raised your hands for aggregation framework. So today, when we're done here, go check out Atlas Stream Processing. Go build yourself a processor. It'll just take you a few seconds. Start it up and see what it does. You already know the aggregation statement. It's pretty common to start small. Just pick a source, pick a sink, let it rip, then say, well, you know what? Maybe I want to match some data. Maybe I want to aggregate some data or whatever. Play with it. Give us feedback. Let us know how it goes. And of course, at the end of the day, it's integrated with Atlas. I told you it's built on MongoDB, so it leverages the reliable and robust database that's been around for many years. It runs as its own service because it's running continuously, but it's integrated within Atlas, just like anything else. It's built within Atlas. Its logging is within Atlas, all of that. So it's something that should be natural. It shouldn't surprise you. It should be something you're used to. Okay, questions?
Thanks so much, Kenny. All right, folks, you down here and bring some microphones over to you. My friend Derek is going to grab you guys over here. Oh, we got one on this side. I'll come to you. Everyone, please excuse me jumping off the stage.
Hello, can you hear me?
Yep, I got you.
Great. So one question I have is how about the, how can it scale in terms of, say, if I want to process thousands of events per second or hundreds of events per second, how am I going to scale this?
Yeah, great question. Great question. So the way the architecture works is that every one of these is built on a separate processor. So when you start a processor and you write an aggregation, that's a single processor. That processor can consume from, like I said, Kafka or MongoDB or whatever, and that alone will do thousands and thousands of documents per second, like very, very fast. Especially when, like, if you're merging into MongoDB, you can do it in parallel. You can read from, you have your own consumer group in Kafka. You can read in parallel from the various brokers from Kafka as well. So it's very fast. That said, we have two things that are coming down the pipe. You can obviously vertically auto-scale this, or auto-scaling soon, but vertically scale it now. So you can go from like an SP10, it's called, kind of like an M10 in MongoDB for database. You can go to an SP10, SP20, that kind of thing. But we're also going to do two new things. One is we're going to auto-scale that in the future, so it'll scale up and scale down. That's not here yet. And then the other one is ultimately we'll do parallel processing. So today there's a lot of techniques. You can pull from various different partitions in Kafka. You can write in parallel merge, like I said. So we're already seeing a really, really high thousands and thousands of records per second kind of performance. But you're right. Like ultimately we need to add parallel processing to have kind of the unbounded scalability. A good question. One thing to point out there though, that you made me think of, the thing I didn't say was, I just want to make sure it's clear that this is a first-class citizen of Kafka. So when you run a stream processor, we're using librd Kafka, so that's obviously very fast. But also, when you run a processor, if there's a failure or something can't connect or whatever, we are checkpointing. So we do keep checkpoints, we do keep state. It is restartable, and that state has to scale. So that's kind of the next piece of work for us. It's a really good question. Did I answer it for you?
Thanks, Doug.
Yeah, thank you.
Okay. Who else? Oh, there's a few over here. Okay, go ahead.
Hey, how's it going? So when creating a aggregation pipeline for publishing events,
Yeah.
from a MongoDB source, like
Yeah.
a collection specifically, does the aggregation pipeline leverage existing indexes on that collection?
Good question. You mean if I have like a partial, like if I'm actually specify a predicate, like, because normally the change stream is anything that changes. So if I've got like inserts or updates, the change stream is going to have that entire log of those. And so you're going to see that. And then you can put like, a match statement or whatever in the pipeline. The one caveat I'll say is you can also do push down. So if I push down a pipeline in MongoDB, then I think at that point it will use an index. Yeah.
Okay, I'll look into it. Thank you.
Hi. I was wondering if you have an aggregate pipeline that goes across collections, do you need multiple change streams and multiple processors to pick up any of the changes, or like how does that work?
That's a great question. So you can specify on the database level or on the cluster level. So you have some choices. You can say, hey, I want one processor for this one collection because it's really busy or something. Or you can say, no, I've got 20 collections in this database. I want all of those into one event stream. Or you can say, no, the entire cluster. So it's kind of up to you to configure the scope of what you want. Does that make sense? I'm not answering your question. Tell me more.
Well, can you like pick and choose? Can you be like,
Yes.
I want these two collections
Yes.
within these other? Yeah,
Yeah.
okay. Then
Yep.
we're good. Thank you.
Yep.
Hi. Thank you. You started to answer my question over here to your right.
Thanks.
You started to answer my question at the very end of the first question, fault tolerance or error handling. If you have a step in the aggregation pipeline that does an HTTPS fetch or some API call, and that errors out 500 error, 400 error, whatever, does it restart automatically?
Yeah, great question. Yeah, great. So I'm gonna take your question and expand it because it's really good. So there's a couple ways that we handle failure in streaming systems. A couple things like the dollar lookup is a good one. $HTTP, that's another good one. These things that might take a few seconds or depend on an external system. How does that work? Well, there's kind of two things. Number one is we kind of have smart defaults here. So it'll try. Let's say you're hitting an API and you're getting 500s or something. It'll ultimately back off. Okay, so it'll try and it'll back off. And yeah, your stream's latent. You can run it. It's in this case it's synchronous or asynchronous. So like you can call a Lambda, for instance, asynchronous, kind of fire and forget, or you can like at the end of your stage, or you can call it synchronous. In the synchronous mode, you're going to wait. The pipeline's going to wait. So it makes sense to kind of have it back off over time. Now, let's say it's getting a whole bunch of errors. We also DLQ. So I didn't talk about the dead letter queue, but the way a dead letter queue, just kind of give a little context there, works is we don't want to leave data on the data center floor, so to speak. So if there's an error processing, maybe you're doing arithmetic and it's a divide by 0 or something like this, you don't get authorized or authentication error to an endpoint, that kind of thing. We'll put it in the DLQ. And so DLQ messages are shown on our graphs. And so you can see like, oh, I'm getting a bunch of DLQs whenever I hit, this endpoint. It's not working, that kind of thing.
Thumbs up.
Okay, cool. One more thing on fault tolerance before you ask that question. Again, we're saving state. And so 2 things. One is it will pick up where it left off in the stream processing pipeline if something does fail. Something in between, like like maybe, I don't know, you can't connect to Kafka or some network error or something like that. It'll pick up where it left off. Also, if you're computing a window and you've got like you're doing math in a group in a window, something like this, it actually keeps that computation. And so it'll start at the end of that computation, not rerun the whole window. So we try to, do proper stream processing architecture from that standpoint.
Does it work only on what has changed, or can you pick and choose what you want to push onto or copy into S3, for example?
Great question. The answer is yes. You can pick everything. So here's how it works. You can set it up so that, like, if I start the stream processor, everything I see from now is an event. So that's like the default way of doing it. There's also initial sync, and initial sync goes back and says, okay, no. I want to copy the entire collection from the beginning of time up to now, then start. And we just introduced this, I don't know, a few weeks ago. It's pretty new, but it works great because what you do is when you start it, you can run it in parallel. You can monitor the progress so you know it's in that initial sync processing time and where it's reading the collection in parallel. Then there's a catch-up phase where like it's writing and then it has a few more messages to catch up to be where it's at, like current time. And then we cut over to current time and it's a regular stream processor from there. So you can do it either way. Does that answer your question? I'm going to follow up.
Sorry. So based on change in one collection, could you copy from another collection?
Okay, so what you would do in that case is, and this is common actually, that's what we would call a Mongo to Mongo use case. So, and it honestly works a lot like a trigger in the sense that if you write data into a collection, you're looking for a particular event, maybe it's like fraud or something, and you're like, hey, based on that, I want to write over here another piece of data and keep that stored, like you're going to change a 0 to a 1 for that customer or something. That's really common, and yes, you can do that. You can write back to your same database, and you can actually put a stream processor on that and continue to compose stream processors.
But you won't be able to, say, archive data if you want to from a particular collection.
You could use this to take, yes, you could. You could take all the changes. You could aggregate them, or you could just leave them. Maybe you don't want to mutate them at all and copy them over to some other system, yes. And you can also write it out to S3, like for cost reasons. So there's a lot of options for that.
Thank you.
That's a good question.
Hi. Following up on scalability and some of the other things that we were discussing. So we have a workflow where we have a change stream. From those change streams, we have to group events together to be handled in order. So kind of against the grain of full-blown scalability. Currently, we basically take those messages and split them up either in an SQS by message group ID or Kafka with different partitions. Is that something that this new system we can just do within Mongo itself? So take those events and kind of have an ordering, but depending on like key or some sort of
great question. Yeah, great question. So yeah, the hard things in streaming are order and time of delivery. Like there's hard pieces of streaming. In this case, yes, you can do it in Mongo, but the way you do it is typically just to use like a Mongo collection. So maybe you set your key on merge, like a primary key correctly, similar to how you might set it in Kafka for the partition for a particular topic, and use MongoDB to do that. That's a pretty common pattern. And sometimes what folks will do is they'll take like a stream of a lot of data and they'll pare it down with some like, match or aggregation. So maybe you've got 1 million messages per second coming in here, but you're like, no, I want to aggregate that down and only show a subset of that. And then I want to put those in order and unique into a collection. That's pretty common. Does that answer your question? Okay.
When would this be available or would it be available in the enterprise edition?
Good question. We get this one a lot. Right now it's Atlas only. Truth be told, being super transparent, I don't have a timeline for anything but Atlas. I will say we do hear that a lot, but we're focused on right now building the proper primitives for stream processing, enabling those use cases I talked about, and down the line we'll get to that piece. I know that's not the answer you wanted. Thank you.
Excuse me. Hey. I have a question. I have 2 questions.
Sure.
So one is Mongo to Mongo. All right. So we have a typical use case where we are doing a Atlas to Atlas migration, and we want to sync the new database where we migrated to the older database, right? So that the existing applications can continue to do it till we finish the migration. We faced a difficulty in stream processing where it is not able to connect to 2 different clusters placed in different organization or project. Is that still a limitation on purpose, or is it something Mongo is going to work on it?
Good question. So there's 2 things I'd advise there. First of all, number one is, so you called it kind of a migration use case. And so I'd be careful there. And the reason I say that is this is at least once processing. So this is not transactional. There's no transactional guarantees here. It's not an exactly one system. It's an at least one system. So you may get duplicates. So be advised. That's how this kind of streaming system works. So just know that. Number 2 is your question was cross orgs or cross project?
It's cross org.
Okay, cross project we just got done. Cross org we call it something different, but we'll get to that point. It's not far off.
Follow-up question, right? Can you please expand on the duplicates, what you have been speaking?
Yeah, so the consistency guarantees so let's just take something like Kafka that's been around for a while. You have different levels of consistency. One of them is faster than the other, and one of them is more accurate, and you can just kind of pick and choose. So in the case of Atlas Stream Processing, right now our consistency guarantee is at least once. So when we restart, you may get a duplicate time event. So like if there's let's see, I'll make it a more concrete example here. So let's say you have Kenny purchase something at a certain time. So that's like, a unique event in the world. That unique event would get maybe played to Mongo. And if there was a fault somewhere in the system, we may reread that from Kafka and it may come back as a duplicate event and it may get reapplied to MongoDB. Now, if you've got a unique key on that, it's just going to say, duplicate key and it's no big deal. So you're solid. And MongoDB affords you that capability by having a unique index. But in the case that you don't, you get 2. So that's why to say your mileage may vary, you want to be eyes wide open about that situation, consistency.
Makes sense, right? Second question, right? So I have another use case where I do Mongo to Databricks, right? We kind of like have our whole content flown through Mongo, and all this content has been like flown to Databricks via Fivetran connector, right? We use a third-party product called Fivetran.
Sure.
We always have this difficulties with Fivetran because Fivetran is one of the things which is pulling us back to upgrade to newer Mongo versions, where Fivetran doesn't support Mongo 8, but Mongo 7 is something going out of life soon. So the use case what we have been seeing in today's session, is it something easier for us to replace Fivetran and go ahead and connect directly from our Mongo content flow to Databricks?
Yeah, so this is, to be transparent, the reason we built $Iceberg was basically out of customer request. Customers kept coming to us saying, hey, we have Databricks or Snowflake or other things, and we need to get the data into those systems, and we need less complexity. That was the real ask. And Iceberg, now you'd have to introduce an Iceberg data store on S3 to do this. And the reason for that is, like, number one, it's sort of a neutral format. It works for lots of things. But number two is it's a good separation of concerns in most orgs between like the Snowflake people and the Mongo people, frankly. So it gives us a nice kind of, intermediate data storage system that they can agree on to use between the two systems. So you would want to add that in this case, and then you'd be good to go.
So the follow-up to it, right, to your answer, the customization what we put in the Fivetran connector for say, so is it going to be applied in the Iceberg in S3 before it sends to Databricks, or will it be applied before even it is being pushed to S3? Where does the customization happen?
You mean if you write a stream processor that has some logic in it?
Yes.
Yeah, that's before. So yeah, great question. So you write the stream processor, it's got a bunch of logic in it. Then you can write it to Iceberg. It's processed that data. Its output goes to Iceberg. So if you redact certain fields or do aggregations or just match only on 10% of your data or something, then that's what you'd have in S3 in Iceberg, and then that could be pulled downstream. This is a great use case because different teams have different data stores. So you might have 2 or 3 of these for different outputs for different teams, that kind of thing. So that's the flexibility we try to build into it. Yeah. So the quick answer to your question is yes.
Thank you.
All right, folks, we'll have time for just one more question here in front.
Hey, I have 3 questions. So, what if the first one is for the S3 bucket for Iceberg table? When you send to the S3, do we send it as a Parquet, or is it compressed, not compressed? How does it work? The second thing, do we have an event table where we have some kind of duplicates that match such certain criteria, and we want, if we can apply this stream to clean it up, like run every 10 minutes, 15 minutes to take this, aggregate them, and write only one of them and then delete them. Is this something we can do it like that? And the third thing is, how is it this cost? How is it billable? Is it by stream, by time, by data?
All great questions. Okay, let me see if I can just keep me honest. So for Iceberg, yes, it's Parquet. The catalog is going to be Hadoop format. You didn't ask about that, but that's kind of the topology. Yeah, so yes to those. Then the next question, let me do it to cost one. It's billed. It's billed per minute. So when you start a processor, the billing starts, and when you stop a processor, it stops. So if you have something that runs once a week and it runs for an hour, that's great. That you just get charged for that. To be honest, a lot of processors just run 24/7. They're just always doing something from A to B. So it sort of depends on the use case. And your other question was?
We have an event, certain events that are duplicate, but the problem is they are not with the real index that we can do compound unique. We need to do some aggregation saying this type. This is a duplicate case that we have from an external system, and clean it up and write it as one record. Is this possible?
So you're going to make me end on the it depends answer. So, okay, I get it. But
yeah,
the answer is depends on use case. And so what you can do in certain cases is you can create a window, so like a tumbling window in your ag pipeline. You can group by a key in there, and then you can use that as and it'll output when that window tumbles, so maybe every hour.
Yes.
And then when that window tumbles, those will be unique keys because you're grouping on it.
Yes.
I made a simple example. Your mileage may vary, to be honest, but that can get you thinking.
And we can delete the source while writing the new output, or we have to do it in another collection.
I think in that case, I'm designing on the fly. This is bad, but I think in that case, you'd want to use like A or B, A or B, or A or B, or something like this.
Okay.
Yeah.
Thank you.
Thanks.
Great. Thank you so much, Kenny. Thank you, everybody, for these thoughtful questions. We'll give Kenny a little round of applause.